going to hear from Jon Stephens, CTO and co-founder of Veridise, an auditing company that builds security tools to help find bugs in all parts of the blockchain ecosystem. He's also a PhD student at UT Austin, where he conducts research at the intersection of programming languages and security. So please welcome Jon.
Hi. So, as was said before, I'm Jon. I'm the CTO of Veridise. Today I'm going to talk to you guys about bugs that we see when zk circuits and dApps interact, particularly at the language level. Okay, so the first place that we're going to start is we're going to look at the different technologies that we're interacting with here. So these are smart contracts and zero-knowledge circuits, and kind of get an idea of the differences between these two things. So zero-knowledge circuits are inherently stateless. You can't store anything between invocations of the zero-knowledge circuit. All inputs have to be passed in, and that's what you're performing the computation on. In addition, control flow is typically restricted. We heard today from a couple of people who have talked about like folding and recursion. However, that's basically the only control flow that you have. You can't have any loops or conditionals or anything like that. Everything is in low-level math. In addition to that, the numeric data type that you're going to be operating over is a finite field. These can be of different sizes, but the important part is they will span from 0 up to some typically relatively large prime. And then the important part, the reason why everyone wants to use zk, or why a lot of people are using zk, is because they will allow you to perform private computations. So inputs to a zk circuit can be kept private, or they can be made public. Smart contracts, on the other hand, are inherently persistent. So you persist state in a smart contract on the blockchain. You can have arbitrary control flow. So if we're looking at like Solidity, you can have dynamic calls and stuff like that. You can do pretty much anything that you want. In addition to that, the numeric data type is a fixed width integer, which means that they're going to be of the size of the power of 2, like a UN256, which is of the size of 0 to 2 to the 256. And then finally, all of the data on a blockchain is public. That's why we interact with a zero-knowledge circuit, so that we can keep some of this data private. So when someone interacts or allows these two technologies to interact, this is typically the way the invocation is going to happen. So this is at a very high level. I've abstracted out some of the parts that we don't need to worry about right now, but essentially you're going to have a user. They are going to invoke the zk circuit with certain inputs. That will generate a proof eventually. And then the proof is what you're going to be checking in on-chain, and once you've checked it on-chain, typically there will be some computation on-chain in order to persist some storage. So today we're going to be looking at how 3 different languages deal with this problem. So in particular, we're going to be looking at a mixture of Solidity and Circom, the Aleo language, which is deployed on the Aleo blockchain, and o1js, which is used for Mina. And so each of these languages allow you to interact with zk and smart contracts. However, they do so in a couple of different ways. So if you look at like Solidity, the storage type that you're going to have is basically a 256-bit integer. You still have arbitrary control flow in your smart contract. However, the logic of your smart contract and your zk circuit are inherently separated because you have to write in 2 different languages, and you have to check in your proof on-chain. And so that's the last part, is when verifying zk proofs, you have to do so explicitly. Your smart contract is actually going to have to go and explicitly verify, yes, this proof was correct, and that's additional logic that the user has to deploy. Aleo, on the other hand, and o1js allow people to store finite fields rather than just integers. They typically also will allow people to operate over integers, but they're specifically integers of a smaller size than a finite field, so that they can model those integers consistently. In addition to that, both of these languages have restricted control flow. And so on the smart contract side, you still can't have the arbitrary control flow or flexibility that you can have in something like Solidity. And so the next part is where they start to differ. So in Aleo, the smart contract logic and the zk logic are still separated. We'll look at an example in a second. Well, in o1js, they're inline. So you express logic once, and then that will be verified on chain. And then finally, Leo only allows implicit verification, which means when I can't explicitly create a proof and then verify it. And so essentially when I create a proof, it's going to be as part of the execution of a Leo transaction, whereas in o1js, I can create explicit proofs and verify them because they allow you to create recursive proofs. So let's quickly take a look at some code just to give you a short introduction to understand the examples. So in the Solidity plus Circom side, I've kind of mixed the Circom language and Solidity language. So what you'll see on top is going to be Circom. What you'll see down below is going to be Solidity. And so you'll see the explicit verification down there. It's always called verify. Leo, the way that they express their logic is the transition function is going to be the zk part of a transition. It can do some things like it can have private inputs, but it can't access any smart contract state. Each transition can be associated with a finalize. The finalize is the on-chain part of your transaction, and it can access your smart contract state, but it can't have private data. Then finally, we have o1js. o1js, everything is just kind of put into a single function, and it will generate constraints from that function, but you can also express on-chain computation. So this first statement, for example, will retrieve a value from on-chain. Okay. So we're going to be talking about a couple of common vulnerabilities that we see when smart contracts and zk interact. So these aren't going to be vulnerabilities that we see specifically in zk circuits. That's another talk we have. Right now we're specifically looking at common mistakes people make when they're integrating zk into a DeFi application. So the first thing that we're going to talk about is missing state validation. So essentially what's going to happen here is because the zk circuit is stateless, the user has to provide state to the zk circuit for verification. However, because the user is providing that state, they can lie. So in the example that you see here, the user might say the on-chain state of x is 0, however, it's actually 5. And so if there is no explicit validation that the state expressed by the user is correct, someone can actually check in state that is incorrect. So if we go back to the example that we were looking at before, we can see how this happens in all three languages. So specifically in Solidity plus Circom, when verifying a proof is correct, if someone doesn't go and validate that the inputs are consistent with the state, then you're going to have an issue where someone can, in this case, can assert that their current balance is something different than what it actually is and essentially mint arbitrary money. In Leo, it looks very similar, where if we aren't validating the state, which is passed into this finalize function, then again, someone can arbitrarily manipulate those values. Finally, in o1js, it looks a little bit different because in o1js, since they have the circuit logic and the smart contract logic in one function, in order to retrieve state in o1js, you actually need to do two things. The first thing is get the state on the smart contract side, but then the second thing is you have to assert that the state that you retrieved is actually equal to the state in the smart contract side. So that essentially enforces the relationship between your asserted value and the actual value in the language in your zk circuit. And so in all of these cases, if you don't do that, then someone can arbitrarily assert that their balance is something else and mint as much money as they want. Okay, so the next thing that we're going to look at is an arithmetic denial of service. So there's going to be two examples that I'm going to show here. So the first example has to do with the different data types that are being stored on-chain. So in this case, an example is an on-chain value might or your on-chain value might have an inflated value that can't be expressed in a finite field. So for example, in Solidity, we talked about how the size of an integer is a uint256, right? So it's 256 bits. However, in Circom, the typical field that people use is can be expressed in 254 bits, which means that if you ever have a value that's above the size of the finite field, that cannot be expressed within your circuit, or it cannot be provided as a value to your circuit, and therefore it can actually break your application. So we've seen this in a couple of cases, but here's an example where someone might, in their constructor, mint the maximum value to a particular user, a sender. However, this is going to actually break your application because you can't actually express uint 256 max in the circuit because it's too large. And so in that case, your circuit is just broken. And we've seen a couple of cases where this has happened, where it's not going to conveniently just break right away. Okay. So now we're going to talk about another type of arithmetic denial of service that can happen because because of the lack of control flow in the other languages that we discussed. So for Leo and o1js, they are inheriting the constraints of a zk circuit within their actual language, which means you can't have arbitrary looping behavior, and anytime you have some sort of a conditional, both sides of that conditional are actually going to be executed. However, both of these languages allow you to express integers that have that restrict overflow behavior. So essentially, they won't allow an integer to overflow. And so what can happen in this case is we've seen where people try to perform some checks in order to see if an overflow happens. So you can see right here where those checks are occurring. But the problem is, even though this looks like it will avoid the overflow, it's assuming that a certain part of these conditionals is not being taken. However, when we are actually executing these in the language or in the ecosystem that they're deployed on, both of those branches will be executed, which means in both cases, this will always overflow, because even though the branch that the overflow occurs in shouldn't be taken, or it seems like it shouldn't be taken, it's still going to be executed, and therefore the overflow restrictions will be triggered. The next thing that we're going to be talking about is finite field overflows. And so these are going to occur because eventually you hit some arbitrarily large value and the finite field is going to overflow. The reason why I'm talking about this here, even though it's kind of a zk specific thing, is because in languages like Solidity, a lot of people will put overflow protections in the smart contract. However, if they're performing this in the smart contract, it's not going to help when people are actually performing computation inside of their circuit, because the data types, again, on the Solidity side are larger than they are on the circuit side. So for example, people will expect that the overflow protections that they have in Solidity will prevent the overflows that they might have in the zk circuit, which again doesn't work because different data types. We can also see these types of issues in Leo because unlike with integers in both Leo and o1js, there is no default overflow check in finite fields, which means anyone who is relying on add and subtract to revert or to fail on an overflow, that will only happen if you're using specific data types like a uint, but it will not work if you are using something like a finite field, which is a little kind of discrepancy that people have to be aware of. Okay, so the next thing that we're going to be talking about is proof verification replay attacks. And so what I mean by this is some of the examples that we have will allow you to explicitly verify proofs. And so for that reason, you have to have some sort of logic which will assert the uniqueness of a proof. And so what I mean by that is you want to make sure that once I have verified a proof on chain, typically you just want that verification to happen once, and you don't want someone to be able to verify a proof a second time. So those of you who are common with zk terminology, this is essentially a missing nullifier check. Okay. So Leo doesn't allow you to explicitly verify zk circuits, but both Solidity and o1js do. And so what we can see here is that even in cases where people might have some sort of validation, so you can see there's a lot of requires on the Solidity side, if you if the validation that you're performing is not good enough in order to assert that your circuit is, or the proof that you're verifying is unique, then someone can replay that. So in this case, even though we have all of these requires, if we're ever back in a state where all of the balances are consistent with the proof that's being verified, someone can actually replay a previous action in order to, in this case, gain funds. All right, so the last type of bug that we're going to be talking about is privacy leakage. So there are a lot of people who are developing on DeFi specific, or who are integrating zk into DeFi specifically because they want to add privacy features to their application. And so for this reason, typically it's very important that any private values that you have remain private. And so let's go to the example. So what we can see is, in this case, we have a private mint function where the goal is to not reveal a user's balance. However, the problem that we have is in all of these cases, there is a flow from the amount that's being minted to some other public value. And so in this case, because the coin wants to track the total supply of the token, once that total supply becomes public, you can tell exactly how much was minted to a user. And so in this case, any time that you have an explicit data flow from a private value to a public value, there's a chance that you could be leaking that value unless you are doing something like hashing. However, there is actually another privacy leak in here, which corresponds to the hash of the balance, because another thing that people can do is, even in cases where you are hashing, someone can perform a dictionary attack or something like that in order to pre-calculate common values and therefore expose a private value. And so one thing that you also have to look out for is not just explicit privacy leaks, but also implicit privacy leaks where someone might be able to infer information through additional context. And so if we look at this particular example, you can see where that happens in this very first line. And in order to fix that, you would need to actually add some sort of a salt or something like that into that hash function. And that's all I have to talk about today. Thank you.
Thank you for a very interesting talk. So I had like two quick questions. You kind of mentioned the possibility of doing like a kind of a dictionary attack, right? Mm-hmm. So in that sense, if you are just doing any kind of tree and any kind of hash function, unless you have the ability to do randomness at that stage, it's kind of impossible to defend against that, right?
No, I mean, that's why people add salts in there. Essentially, as long as you add in some sort of random value, and a lot of the times they put this in control of the user.
Yeah, it becomes non-deterministic in that sense of speaking. So that becomes one set of challenges. The second bit I wanted to ask was, I've come across these race conditions, right? Mm-hmm. And I was wondering, can you, so literally race conditions in normal Web 2 mm-hmm. is, you know what it is, right? I've been in security the last 25 years. So I've seen the same thing happen between zk and circuits. So you have two sets of logic and you have a race condition, and if that happens, what would your recommendation would be to do the best you can do? That's what I'm asking.
Yeah, so I'm not sure if this is the context that you're talking about, but one thing that we've seen occur frequently is there are race conditions in state that you have on-chain. So for example, the root of a tree, and then if you have people who are interacting with your contract very frequently, then the root of the tree that you have is going to change frequently, and therefore users who generated their proof or started generating their proof where you had one root won't be able to verify it because now the root has changed. There's a couple of things that we've seen there. Typically, what we look for in those cases is people main a history of roots that they have over the past, or the previous n roots or something like that, and then they allow updates to happen over those previous n roots. However, that doesn't always work. It depends on the actions that you're allowing a user to take, and so in some cases, you either need to add additional state about what was being added to the tree so that you can validate that, yes, they were making a modification off of a previous root, and then update the tree in place in your contract is what we've seen most often. because it's the update that is the thing that's hardest to deal with, because if you have an old root, then someone could overwrite a value when they check in a new root. And so typically we see people on the smart contract side maintaining their own tree or having their own tree and then inserting the leaf into the on-chain tree.
Thank you.
But it's more expensive.
Yeah, have you done your security analysis on the other GKVM, like the RISC-0 Bonsai? I mean, does it have similar security loopholes issue that you mentioned, or maybe?
Right, so different languages are going to have different trade-offs. So RISC-0, because what they do is they essentially interpret arbitrary RISC-V code, and they really, there is no reason for you to actually check that in on chain. That's something that you can do. But essentially, they're just generating a proof that you actually executed this arbitrary RISC-V code, right? And generating a circuit. And generating a proof. So in this case, some of the vulnerabilities that we talked about in here can occur again. So if you're using this in order to interact with blockchain, the missing state validation in particular is going to be something that you need to worry about. I can't remember. So these are the three languages that I'm the most familiar with. I don't think that RISC-V allows you to have private values, but I don't remember.
No, it does.
Okay. So in that case, privacy leakage is another thing that you would need to worry about.
What about the finite flow, overflow thing?
No, so RISC-V, I believe, is going to be executing over integers, and so in that case, you're not going to have a finite field overflow. However, you can have an integer overflow. So essentially, you can still have an overflow at normal boundaries. So one of the things that we see, particularly with the finite field overflow, is developers don't expect an overflow to occur at like a boundary that's a prime, and so that's where things become a little bit complicated. But yeah, so those are the things that you would have to look for in something like RISC-V.
All right, thank you.
All right.